Okay.
Okay.
No. I just want to tell you that I have a meeting at 11:45 my time. About 1 hour and 15 minutes, so we should finish. Try to
Yes.
finish the
Yeah. So without any further ado, I will like my friend Atish over here to start this talk.
All right. Am I audible?
Yeah.
Okay. So welcome back, everyone. The lecture we have now is by Professor Atish Dabholkar, and we extend the warmest welcome to you, sir. And I would like to ask Prabhanjan Kulkarni to introduce him.
Thank you, Adishri. Professor Atish Dabholkar is a renowned theoretical physicist. He became the 5th director of International Center for Theoretical Physics in November 2019. He completed his graduation from the Indian Institute of Technology, Kanpur. He earned a PhD in theoretical physics from Princeton University, followed by a postdoctoral and research positions at Rutgers University, Harvard University, and the California Institute of Technology. Until 2010, he was a professor of theoretical physics at the Tata Institute of Fundamental Research in Mumbai and has been a visiting professor at Stanford University and a visiting scientist at CERN. He joined ICTP in 2014 on secondment from Seaborn University and the National Center for Scientific Research, where he has been a research director since 2007. At ICTP, he was head of the High Energy Cosmology and Astroparticle Physics section. Professor Dabholkar is well known for his research on string theory and quantum black holes, including investigations that built on ICTP founder Abdus Salam's Nobel Prize-winning work on electroweak unification. He has received many honors, including the Shanti Swarup Bhatnagar Award in 2006. He is an elected member of the Indian Academy of Sciences, and in 2007, he received the Chair of Excellence Award from the National Research Agency in France. We welcome warm regards, sir, and I would like you, if you could start your talk. Thank you.
Okay, thank you, Prabhanjan. ओके नमस्ते. मला इथे येऊन विशेष आनंद होतोय कारण मी फर्ग्युसनचे माझे जुने ऋणानुबंध आहेत अशा अर्थाने की मी 11वी 12वीत तिथे होतो पुण्यामध्ये. सो आय एम व्हेरी हॅपी टू रिटर्न टू अल्मा माटर. And it's very good to see so many young people interested in physics and learn a bit about your Astro Club. So today I'm going to tell you, and I hope I have tried to keep this discussion reasonably at a level that is, I think, if it with a reasonable background in physics, I hope you'll be able to follow everything. Okay, so there has been some very exciting developments in understanding the structure of the black hole, both at the classical level and at the quantum level. And I would like to first introduce you a bit of some of the essential concepts that go into defining what is a black hole and why black hole is such an interesting object. It's certainly a very bizarre object, but why is it interesting from the physics point of view? And why do we want to study the quantum properties of black holes? And surprisingly, it goes back to the work of Hawking, Stephen Hawking. As you perhaps know, Stephen Hawking visited India when I was at Tata Institute many years ago. And some of the questions that you ask in the context of black hole physics naturally lead to some very, you might have thought, abstruse mathematics of Ramanujan, which he created 100 years ago. So it's actually a very interesting confluence of ideas, all the way from astrophysical objects like black holes to number theory, where somebody like Ramanujan has made, as you know, very original and deep contributions. So there is an Indian connection to that. Okay. So let me remind you a little bit about relativity. So the word relativity means the relativity of simultaneity of time, the two events which look simultaneous. Before Einstein, it was understood that there is an absolute notion of time. So if you thought that two events were simultaneous, somebody moving in a train would also think that the two events are simultaneous. And the time measured by you and somebody moving in a train would be, your clocks would run at the same speed, would show the same time. But one of the important things that Einstein realized was that speed of light, if it is measured whether you're on a platform or on a train, is always a fixed value, which, as you know, is like 300,000 kilometers per second. So whether the train is moving or not, I mean, whether you're in a moving train or on a platform, the speed of light is always constant. This is actually very surprising if you think about it, and the physics students here would know that it's very surprising. Because if you throw a ball, for example, in a train at some velocity, let's say at the same speed as at which train is moving, then for a person who is sitting on the platform, it would look like the ball is moving at twice the speed, because you will add the speed of the ball and the speed of the train. So for a person who is on the train, the ball would seem to move at twice the speed. So it's very bizarre that the light somehow does not behave like that. And that has to do with the fact that time actually runs a bit slower in moving frames. And in fact, it's very easy to see that if the speed of light is constant, then it has to be that the time runs slower, because suppose you have a mirror and you shoot a laser beam at it and the laser beam comes back to you and you are in a train. But from the point of view of a person on the platform, if you shoot a laser beam, the mirror, because the train is moving, the mirror would have actually moved further down. And so the distance that the light beam has to travel to the mirror is actually larger, and therefore the time would be larger. So by this kind of reasoning, and actually more or less just by applying Pythagoras theorem, you can essentially derive this notion that time is relative and times run slower or faster depending on whether you're moving, in such a way that the speed of light always remains constant. So this means that the speed of light, actually, this one of the implications is that is the ultimate speed limit. You know, it's like on every highway in a physical universe, you can never cross 300,000 kilometers per second, no matter how powerful are your rockets. So this has two very dramatic consequences. One consequence is gravitational waves, and the other consequence is black holes. So I will describe both of them. So why gravitational waves? Actually, Einstein, more or less, as soon as he discovered this special theory of relativity, understood that this doesn't fit well with Newton's law of gravity. Because if you recall Newton's law of gravity, it says that the attraction between the sun and earth is, do you remember? It's the inverse square law, right? Always, instantaneously. This is very, very strange, because according to Newton, the force of gravity exists instantaneously. It's always there, as long as the mass is there. So then the question you might ask, that what happens if the sun would disappear? Suppose somebody destroyed the sun, just a thought experiment. When would we come to know about it? According to Newton, we will come to know about it immediately, because the force of gravity is the inverse square law. Mass of the object, if the sun has disappeared, then that mass has gone to zero. And therefore, so the inverse square law, if you remember, would be mass of the sun times mass of the earth divided by the square of the distance between earth and the sun. But if the sun disappears, the force would just drop to zero instantaneously. So force of gravity acts instantaneous. And actually this bothered Newton himself. Newton was very bothered by this fact, and many of his contemporaries criticized him. That how can you have something acting instantaneously, action at a distance? And Newton being Newton, he understood that this is not exactly, cannot be completely correct. Because it would mean that if I wave my hand, or if we shift the mass distribution on Earth the gravitational force would change instantaneously. And this bizarre behavior was actually corrected by Einstein. Because if you know, light takes about 8 minutes to reach from the sun to Earth. And Einstein's theory implied that even gravity cannot travel faster than the speed of light, because speed of light is the ultimate speed limit. And in fact, gravity actually travels at the speed of light, the gravitational waves. And therefore, the force of gravity also reaches us after 8 minutes. So we will come to know about that the sun has disappeared only 8 minutes later. Second consequence is the black holes. So as you know, a rocket can escape gravity if it goes fast enough. So for example, if you are on Earth, if you throw a stone, then it will fall some distance. If you throw it harder, it will go a bit further. If you really throw it fast enough, then it will be like a satellite and it will start going around Earth in orbital velocity. And if you really throw it even faster than that, then it will escape the gravitational pull of Earth, and it would be like a rocket going to the moon. And you might think that, therefore, you have to keep throwing faster and faster as the object, like instead of Earth, if you're on Jupiter, the escape velocity is even higher. Now, what would happen? You can just ask yourself this question. If you had enormous mass compared to the Jupiter, let's say billions of solar masses, then the escape velocity could even be bigger than the speed of light. And then what is supposed to happen? Can we escape the gravitational pull of such a gigantic star? And again, if you really believe in this ultimate speed limit, then it cannot happen. So therefore, even light cannot escape the, cannot escape the gravitational pull of a black hole. Sorry, gravitational pull of a heavy enough star. And that object is called a black hole. So this is artist's impression of a black hole. And it is surrounded by what is known as an event horizon. The event horizon is sort of the boundary of the black hole. Okay, but it's a very strange kind of boundary, you know. At some level, it looks like a boundary. It's like a wall, you know. So if you can cross the wall. But it's a very funny kind of a wall. It's actually moving at the speed of light. It's a strange thing to describe in words, but it's a object which is like a stationary object, but which is like a wall, but it's in fact it's moving at the speed of light. So what happens is that as soon as you cross this wall, cross this event horizon, you cannot come back, because to come back, you would have to overtake the wall or the event horizon, but the event horizon is moving at the speed of light. And since you cannot travel faster than the speed of light, you cannot actually come out. So it's a bit like, it's a one-way surface, you know. You can come to this seminar, but you cannot leave. Okay. In a physical seminar room, this is a good joke, but you know, you are on a Zoom, so you can leave anytime you like. So it's a one-way surface in which you can fall in, but you cannot come out. And what happens for the person who falls in? Actually, for a while, that person may not even realize that she has fallen inside a black hole. It can happen that something really evil happens to her in her future. So somehow, the singularity that people talk about inside of a black hole is not some singularity out there, but it's in your future. So these are some of the very bizarre properties of black holes and it happens because the fact that there is a ultimate speed limit, which is the speed of light. Once you fall inside, since you cannot escape out, what was your time actually looks like space actually. So there is some kind of a switch between space and time in some figurative sense. Basically, you have some very strange causal properties. So black hole is this very bizarre prediction of Einstein's equations of relativity, general theory of relativity. If you solve them, one of the equations is this black hole solution. And it tells you that the causal properties of space and time are sometimes can be very strange. And they can be such that there are regions in this space and time. Once you fall inside that region, you cannot come out. And that's called a black hole. In fact, there was a big debate about whether black holes even exist. Einstein himself wrote a wrong paper claiming that black holes cannot exist in the physical theory. So it just tells you that it's an interesting study in the history of science, that it's not that science doesn't progress in one direction. You know, people make mistakes all the time, and even great scientists make mistakes all the time, and you have to correct it. And so therefore you don't take anybody's word for as a revealed wisdom, even including Einstein. And one of the major results was by actually Chandrasekhar. You perhaps know the Chandrasekhar limit, that if your star is sufficiently big, if it's a bit bigger than the sun, and suppose it runs out of nuclear fuel. Now, you know about our sun. Our sun is being kept, it should actually collapse. But what happens is that as it starts to collapse, the core of the sun starts to heat up. And it basically starts a nuclear furnace inside. And as long as that nuclear furnace is burning fuel, there is like explosions happening. And the pressure from that nuclear furnace, the hot gas that is created, that pressure balances gravity. So the sun cannot really collapse. But eventually, the nuclear furnace will run out of fuel. For example, the hydrogen will turn into helium. It's a fusion reactor, basically. There is a lot of hydrogen, which is turning into helium, and the helium can combine. Effectively, eventually, when all the fuel runs out, gravity doesn't stop. I mean, gravity is inexorable pull or push inwards, will basically make the star collapse. And Chandrasekhar derived a limit that beyond a certain mass, it's about 1.4 solar masses. So it's a star slightly bigger than the sun, will always gravitationally collapse. And it will therefore form a black hole. And this conclusion was so bizarre that many leading astronomers and physicists like Eddington and Einstein refused to believe it for decades. And it took several decades before this very almost obvious conclusion now of Einstein's own equations. These are called the famous Einstein equations. It's a very more or less straightforward consequence. Was not accepted by the scientific community. But now, and in fact, actually, as late as 1970, even then Hawking and Penrose and several other, Israel Carter, they proved some very important theorems to show that existence of black holes is very generic in Einstein's theory of relativity. And more or less all the time you will have black holes. But a large part of the astrophysical community and astronomers thought that this was just some useless theoretician's fantasy. Except for a few really visionary people like who went for this LIGO experiment, which got the Nobel Prize a couple of years ago. And what they observed is really, really spectacular. So Kip Thorne was at Caltech, and when I was at Caltech, actually, even I myself, I didn't think, many of my colleagues, I mean, in the theoretical community, didn't really think that the LIGO experiment had a chance of succeeding any time in our lifetime. But people like Kip Thorne sort of really kept at it, and many of his colleagues. And of course, as you know, now India is part of this. Indigo is a LIGO-like experiment in India that is going to happen. There are now many gravitational observatories similar to LIGO coming up around the world. And what they observed was a collision of two black holes turning into a single black hole. So this is a movie that I will run for you. These two black holes are sort of circling into each other, and they're losing energy. And then they form a big black hole, and then everything stops. So this is really spectacular and amazing. And this actually happened 1 billion years ago. So what we saw, this is a simulation, of course, it's not what you observe, but these little dots that you're seeing were the stars in the background. And as the black holes are moving, the gravitational field changes, and because of this gravitational, you sort of the stars, the light gets bent, and it looks like the stars are moving all over the place. And then the black hole comes and forms a bigger black hole. But in the process, what happens is that it loses a lot of its mass. And that entire mass is converted into gravitational energy. And that flash is so powerful, actually, that so much energy is radiated that it completely overpowers, in fact, the energy of all the visible stars for that fraction of a second. So it's one of the most powerful explosions. But of course, you don't see it. It's in gravitational waves, which sort of just pass through your body. And it happened 1 billion light years away. And that gravitational wave has been traveling for 1 billion years. And it somehow got detected in this LIGO experiment. It's a very amazing laser interferometer experiment, that you have a laser beam and you have interference patterns, roughly speaking. And people were able to actually measure. So when the gravitational wave passes you, it sort of disturbs the space-time, disturbs the distance between this of the interferometer, and there is a shift, and that's what people measured. Okay, so that's a relativity. Now, relativity describes nature. So already it is classic. This is called classical general theory of relativity, and that's already a huge subject. And very beautiful results have been obtained in classical general relativity. And and now with gravitational waves, there is an explosion of interest. There is another aspect, and one could spend several lectures on this. Perhaps you heard a lecture from during this series. Probably one of the lectures was on this topic. I don't know. Now, relativity describes nature at very large distances, all the way from the solar system to the universe, or to exotic objects like black holes or pulsars and so on. And as I told you, it generalizes Newton's law of gravitation so that gravity cannot travel instantaneously. Gravity travels at the speed of light. It predicts gravity, waves, and black holes. But this is only one part of the story. This is the black hole part of the story. What about the quantum part of the story? Now, quantum theory, as you know, describes nature at very short distances in the opposite limit. And this, again, has been enormously successful. I mean, it's hard to describe to a non-physicist how amazingly impressive are the successes of quantum theory. In describing atoms, molecules, physics of the atomic nucleus, all of this can be described in terms of quantum theory, in terms of interactions of fundamental particles like electrons, quarks, and photons, and so on. But it also has somebody has said it jokingly, that 1/3 of the American economy depends on the Planck's constant. Planck's constant is one of the fundamental constants of quantum theory or on quantum physics. Because it underlies much of the modern technology, from semiconductors to lasers. One of the consequences of quantum theory is that energy is quantized. See, normally when you throw a ball, you can keep throwing it faster and faster continuously. You can increase the speed continuously. Not so for electrons which are moving inside an atom or inside a semiconductor. So there are gaps, and these are the gaps that you use. I mean, there is a gap in the energy, in which if the energy is smaller than the gap, then the electron cannot actually go anywhere. This sounds very bizarre, actually, but this is one of the bizarre consequences of quantum theory. And that's what underlies the semiconductor physics, or the lasers that we use, in the remote that we use. The lasers are, again, require quantum theory to understand properly. So more or less, all the technology that we use, and the mobile phone, and in fact, the Zoom that we're doing, really could not have been possible unless we understood quantum physics. And it has some very striking consequences. For example, it predicts an antiparticle for every particle. If you put quantum theory together with Einstein's relativity, then it's a fairly easy consequence to see that if you have an electron, you have to have an anti-electron, just if you want to have a causal theory. And this very dramatic prediction by this great theoretical physicist Dirac was verified experimentally. And now we routinely make antiparticle beams in laboratories. Now, here we come to the crux. I mean, it's sort of now where the modern research, including mine, is focusing their energies on. So in spite of this enormous success of both theories in their respective domains, there is a fundamental and a very serious contradiction. And roughly the contradiction is that if you try to compute, normally what happens is that because of quantum theory, your classical behavior gets modified a little bit. But if you actually try to compute, but not a lot. So if you try to combine quantum theory with, let's say, Newton's law of gravity or Einstein's theory of relativity, then instead of finding that there is a small correction to the force of gravity between the sun and the earth, you expect it to be small. After all, it's a correction. It's some quantum effect. You get actually an answer that is infinite. So this is a very, let's say, pedestrian way of describing this fundamental contradiction between general theory of relativity and quantum mechanics. That a small, what you think should be a small correction to, let's say, the force of gravity between the sun and earth, if you actually do a calculation, you get an infinity. And this is something, it's clearly not true experimentally. So if you cannot apply quantum mechanics to gravity, so it seems. But actually, quantum theory has this property that you either treat everything quantum mechanically or you cannot treat anything quantum mechanically. So you don't have this option that, okay, things in this room I will treat quantum mechanically, in another room I will treat classically. So this is really a really very fundamental contradiction, that keeps theorists like myself awake at night. And people have not been able to successfully overcome it for a very long time. So this is what is known as a quantum gravity, that these two cornerstones of modern physics, which are relativity and quantum theory, can we put them together? Both work very well in their respective domains, but they are mutually inconsistent. And can you find a consistent framework that unifies the two? And this has inspired a lot of research. And one of the famous results is that black holes are actually hot. I mean, both from the point of view of being really sort of from the intellectual point of view, they're a hot topic of research. But Hawking discovered that because of quantum effects, black holes are actually not really black. Classically, they look black because nothing can escape. But they are actually slowly emitting radiation, and that's called the Hawking radiation. So they look actually rather like a hot piece of metal. There is a very remarkable connection between relativity and quantum theory. Now, you must ask this question, me, how can this be possible? Because I just now told you that event horizon is this surface where something falls in. I mean, you cannot violate the fundamental speed limit, the speed of light. So how is it possible that something can come out of the black hole? And the answer is actually quite subtle. What is happening is that things are not exactly coming out of the black hole. It's all happening near the event horizon. So as you know, because of particles and antiparticles, in fact, as we speak, constantly in this in this room also, particles and antiparticles get created, they live for a little while, and they get destroyed. This is happening all the time. So what we think as nothing is actually very complicated. The vacuum in quantum field theory is a very complicated object. And when you say that it's total vacuum, is actually there are all these pairs are being created, particle-antiparticle pairs are being created, and they're getting destroyed. So this is constantly happening. Because of that, what can happen is that once in a while, one of these pairs, which is very close to the event horizon, can fall into the black hole, and its partner can escape to infinity. And because there is a little bit of quantum uncertainty, where exactly is the event horizon is not certain. So quantum theory allows for that little bit of a fuzziness around the event horizon. And because of that, sometimes particles can fall inside. And that's what leads to the Hawking. So it actually doesn't violate the Einstein's fundamental speed limit, but it nevertheless makes it possible that the black hole can radiate. In fact, the black hole has some temperature. And Hawking was able to compute it precisely in terms of the mass of the black hole. In fact, the temperature is inversely proportional to the mass of the black hole. So the heavier the black hole, the colder it is. If you take a really small black hole, it will be extremely hot. So if you take a astrophysical black hole, basically this temperature is very, very negligible and you don't have to worry about it. Now, in atomic theory, this raises a puzzle though. In atomic theory, we understand the temperature in terms of motion. I mean, if you like, if there is a one-line summary of modern physics, can somebody tell me the one-line summary of the modern physics? One-line summary of modern physics is that everything is made up of atoms. And you can understand all physical phenomena in terms of motion of atoms. Okay, atoms defined in some broad sense, elementary particles. This is a very powerful statement. So all notions like color, temperature, softness, smoothness, everything you can reduce fundamentally to the motion of the basic constituents of matter. In particular, you know very well that when a metal is hot, what is happening is that the little atoms that make up the metal, let's say the iron, they are jiggling around very fast. They are vibrating. And as you heat the temperature, they start jiggling around even faster and faster. At one point, they are held together by an chemical bond between the two. If they start jiggling around too much, beyond a certain temperature, they just fly away. And that's when the metal starts to melt. So atoms vibrating faster is when the metal is hotter. How can we explain now the temperature of a black hole? It's really space-time. There is nothing. It's a black hole in the space-time. There is nothing there. There are no atoms. So the question becomes, what is the analog of the atoms that makes up a black hole in space-time? And the answer to this question is what actually leads to some of the research that I have been involved in, to string theory and ultimately to Ramanujan, as I will explain. So a very fundamental concept that I want you to remind you is that of entropy. And you might have studied this in your course in thermodynamics and as something very complicated or something not so interesting. But it's really one of the most fundamental concepts in modern physics. It's one of those, it's actually very, one of those few examples where Carnot, who was an engineer actually trying to design steam engines, made some really fundamental contributions to physics. It's a very subtle and profound concept. And what they were trying to explain was, why does heat flow from a hot body to a cold body, but not the other way around? Because if you could do that, then you can make a perpetual steam engine. So there is some kind of irreversibility in nature that heat can only flow in one direction. It cannot go the other direction. How can you quantify this irreversibility? And that's what leads to this notion of entropy. And I can give 4 lectures just explaining what is entropy. It's a very beautiful topic. So you define the quantity called entropy as follows. If you add some heat to a body at some temperature, let's suppose you have a piece of metal and you add, or let's say gas in this room. If you put a heater in this room, then you're adding some heat to this room at room temperature, which means that you're also adding entropy to this room. And that entropy is equal to the amount of heat that you have added divided by the temperature of the room. So it's a very simple concept. You can actually calculate it because you can look at how much heat you have added by looking at how much electricity you have used and divide that by temperature. That's the change in entropy. So what's so fundamental about this concept? What is fundamental? There are many things, many aspects of it. One is in irreversible process, the net entropy always increases. This you probably know, the second law of thermodynamics. I mean, I'm sure the physics students know, but even others, if I remind you, there is this thing called the second law of thermodynamics. And I think every literate person should know about it. In the same way that as every literate person should have heard about, I don't know, famous pieces of literature, like Shakespeare or Mahabharata, So entropy is an intrinsic property of a given system, and it's a function of energy. And the change is always positive or equal to 0 in any natural irreversible process. And hot bodies also have entropy, and black hole also must have entropy. So every hot body must have entropy, and a black hole also therefore must have entropy, because entropy is an intrinsic property of a given system. So like for the gas in this room, the air in this room, that air has some entropy. When you heat it up, that entropy goes to some other value. It's again, but it's an intrinsic property of this gas in this room. Now you can very easily explain irreversibility. See, if the heat delta Q flows from a body at temperature T1 to a body at temperature T2, the net change in entropy is absolute value of delta Q, because when the body which loses the entropy, you put a minus sign there. So the body at higher temperature T1 was giving out the entropy, so it's minus, and the body which was gaining the entropy at temperature T2 it's gaining in entropy. And now it's clear that if entropy is always positive, change in entropy, then heat can only flow only if T1 is greater than T2. So that explains this irreversibility that is very fundamental in nature. That if you run, suppose if you scramble an egg, it's much simpler. And if you run the film backwards, nobody will believe you that the pieces of the egg somehow assemble naturally back to a whole egg. That's because it cannot happen in any in a large system, in a macroscopic process, where the entropy decreases. But there is a very fundamental reason why entropy is very fundamental for physics, and that is that. So now I'm going slightly into technical details, and I hope this is meant for the physics students, so not everybody will maybe able to follow. But okay, I have to also put in some equations. Boltzmann, one of the great physicists of 19th century, in fact, he had a kind of a tragic personal life, because nobody actually believed in the reality of atoms, especially the chemists didn't believe in the reality of atoms when Boltzmann was talking about it. So until his death, nobody actually believed. And it's hard for us to believe that. I told you that the fact that the world is made up of atoms is one of the fundamental consequences of, one of the fundamental principles of physics. Something so fundamental that we take it for granted now. 100 years ago, there were doubts about it. So this also tells you how science evolves. And what Boltzmann said is that the entropy is related to the number of different states the system can be for a given energy n. And there is a famous Boltzmann relation that the entropy is basically proportional to the logarithm of the number of ways in which you can assemble the system. So basically, it's the number of different ways you can partition a given energy. So what do we mean by this? Like in this room, suppose the total energy of the room is given to you, then there are many ways you can have the same energy. You can have one atom going that way, another atom going that way. Or you can have one atom going much faster in this way, another atom going a bit slower in this way. You can basically just count how many different ways are there in which this system can be, given the fact that there's some fixed energy n. And that is supposed to be entropy. Now, this is a very, very fundamental observation. Why? Because as I told you, energy I can measure, entropy I can measure just by measuring the what is happening, how much heat I have given. Using experiments, like I take a heater, I measure how much electricity is used and what is the temperature. These are all very macroscopic experiments. I have a big thermometer, a big heater. But from that, I can deduce some properties about the atomic structure of this room. Now, this is very powerful because, you see, all of us believe, but if I ask you, all of us believe that this room is full of nitrogen molecules or oxygen molecules, right? We are breathing air. If I ask you, how do you know this? You don't really know this. Is there a microscope under which you have seen little atoms? And certainly not in the 19th century. There was no microscope powerful enough to see the structure, atoms moving around. So how do we know that actually the world is made up of atoms? Or how do we know that this room is full of atoms? It's through Boltzmann's relation. Because once you are able to calculate entropy using macroscopic properties, you can compare it with experiment, and that way you try to build a microscopic picture of what is happening in this room. And Boltzmann gave this very important connection, and this explained irreversibility as a statistical tendency towards disorder. So his idea was that entropy increases not because of some fundamental property of the laws of motion, but it's simply because there are many more ways in which the entropy is larger. So just to give you a simple example, if you take a jigsaw puzzle, there is only one way the jigsaw puzzle is in a state which you would call the jigsaw puzzle is properly assembled. But there are many different ways in which the jigsaw puzzle is broken. There are thousands of ways in which the jigsaw puzzle can be all mixed up. And therefore, generically, if you take a box and you shake it, it's highly unlikely that spontaneously the jigsaw puzzle will assemble itself. Just by statistically, not because there is no fundamental law of nature which tells you that jigsaw puzzle cannot assemble itself, or it is more likely not to assemble itself than it is. But it is in a statistical sense, because there are many more states in which the jigsaw puzzle is broken, and there is only one state in which the jigsaw puzzle is assembled. And simply because there are hugely more states when it is broken than when it is not. And it's the same thing works for hot bodies. When it is hot, there are many more ways. So the entropy is bigger or smaller. You can sort of relate it to the number of ways in which the system can be. Now, what does it have to do with black hole? Well, as I told you, black holes are hot. So like every hot body, it should also have entropy. And Hawking, in fact, did a very beautiful calculation following up on earlier ideas of Bekenstein. And he got a very beautiful general universal formula that the entropy of a black hole is area of the black hole. So I told you there is a horizon. So horizon is this kind of a surface or two-dimensional surface. You calculate the area of that. Suppose there is some radius of that surface. 4 pi r square is the area of that surface divided by 4. That is the entropy that you associate with the black hole of a given mass. And this checks out with Hawking's earlier calculation that the temperature is inversely proportional to the mass. Because if you actually, you can write down this first law of thermodynamics involving black holes. But that raises a second puzzle, that can we actually explain this entropy in terms of counting of something? Because I told you, Boltzmann has told us that everything, all entropy must be explained in terms of the number of ways you can assemble the system. Entropy is equal to logarithm of the number of ways in which you can assemble the system for a given energy. And that's where string theory comes into picture. String theory postulates that the fundamental constituents are not point-like, but they're string-like. They're moving in 10 or 26 space-time dimensions. When I say space-time dimension, there is one is always time. So it has 25 plus 1, 25 spatial dimensions and 1 temporal dimension, or 9 spatial dimensions and 1 temporal dimensions. And this is one of the most promising candidates for a unified theory of quantum gravity. And in fact, some of these very deep puzzles that I told you about, which have to do with unifying general theory of relativity and quantum mechanics, get resolved in string theory in a very non-trivial way. And this is one of the reasons why many scientists around the world, including myself, have been taking string theory very seriously for the last several decades. And the idea of string theory is that the string can oscillate in many different ways. Now, this idea looks actually almost childishly simple, but there is actually quite deep mathematics behind it. And when you try to actually describe a relativistic string in this way, you discover a lot of very surprising facts. First of all, it turns out that many different elementary particles like electrons and protons, quarks, and you can describe as different ways, the string can oscillate. The different musical note produced by, think of the string as a sitar string. Different note produced by the sitar string will correspond to a different elementary particle. So if you have a sa, then it corresponds to an electron, and if you have a ray, it corresponds to a quark, just to simplify. And this actually unifies all particles. It has a potential to unify all particles. I should tell you that string theory is still a work in progress. So we don't have direct experimental confirmation of string theory. So it could turn out to be wrong. But there are quite powerful, deep results about the structure of quantum theory of gravity, where string theory seems to do astonishingly well. And so there is a lot of confidence sort of in the intellectual coherence of this structure. And that's why many people take it very seriously. So everything should be made up of the string. So even a black hole can be made up of an oscillating string. But you might ask me, what about these extra dimensions? Because we live in 3+1 dimension, right? We don't live in 9+1 dimension. Or we have only height, length, depth, and time. If you denote these dimensions by 1, 2, and 3, height, length, depth is 1, 2, 3, and time is 0. Then consistency of string theory requires that you have additional dimensions like 4, 5, 6, 7, 8, 9. These extra dimensions, the way it is postulated, and currently we don't fully understand it, but I mean, we understand it. We have scenarios in which this can happen, that they are curled up into small compact balls, and we don't see them in our daily life. However, we can actually see them using black holes, because near a black hole, these little balls, the space which is curled up, can actually have consequences. Just to give an idea, if you have an insect moving on a thin wire, right? Suppose you're an insect moving on a thin wire, copper wire. That insect can only move in one direction. I mean, only go along that wire. So for that insect, the wire would look actually to have just one dimension. And because the other dimension is kind of curled up into a small little thing, if you had a small object, it could go around that thing. But for a fat enough insect, that insect would not be able to really figure out that it's moving on a 3-dimensional object. So that's the basic idea of this compactification, that roughly speaking, this 0, 1, 2, 3 are along this longitudinal, it's like moving along the longitudinal wire. And 4, 5, 6, 7, 8, 9 are sort of around this, moving around this wire. Is this clear, or are there any questions at this point? So far, so good. Please feel free to ask questions. Maybe I will take a pause for 1 minute. Okay, if you prefer that, okay. So as to move fast, actually, we are running a bit out of time. Yeah, I think it's a good idea. So for a class of black holes, which can be described in terms of oscillating strings, so since you have a string, the string is actually oscillating, it turns out. If you're in 26 dimension, now this particular example is in 26 dimension, then the string takes up 1 dimension and the time takes up 1 dimension. So you have basically 24 transverse dimensions in which the string can oscillate. And the total energy of that oscillation is fixed by the mass of the black hole, and that's n, let's say. The question becomes, how many ways can this string oscillate? This way, that way, it can oscillate in 24 different ways. So we have to calculate the number of ways you can actually divide this energy, the total energy n, in a way that the string can oscillate this way, that way, in long wavelengths, in short wavelengths, and so on. And this actually reduces to the problem of counting states. And this problem, I will skip this slide, relates to some very interesting mathematics that Ramanujan was interested in for his own reasons. And Ramanujan is among the all-time greats like Euler and Gauss, who made really profound contributions to number theory. You might have seen this movie, The Man Who Knew Infinity. He's really somebody of singular gifts and remarkable intuition for numbers. And he inspired ideas which have kept mathematicians busy for many, many years. And some of his work actually came surprisingly to our rescue when I was thinking about some problems in black holes. And it turns out that the mathematics that was needed was something that Ramanujan had created many years ago. So just to give you one such an example is that if you take a integer like 3, let's say, and you ask the question, how many ways can I partition it? I can write it as 1 plus 1 plus 1, 1 plus 2, or 2 plus 1, or just as 3. But I can now make it more complicated. Suppose I'm allowed to use 2 different colors. Then I can write it as 1 plus 1 all green, or 1 plus 1 all brown, or 1 plus 1 green plus 1 brown, etc. So there are many different ways And this is the counting problem that Ramanujan posed himself. And he found a very beautiful answer, that he said that, look at this function as a function of Q. So the problem that is interested in the string theory is that now suppose I give an integer n with 24 different colors, okay? Instead of just 2 different colors, 24 different colors. How many ways can you get that integer? That's a very simple counting problem, right? And that answer to that question is given by this calculation of Ramanujan, that you basically is given by this what is known as the partition function. That you take this function and look at the coefficient of q to the power n of this function, and that is the number that you are interested in. And this number is exactly the entropy of the black hole. Just to give that number, if you take the logarithm of that number, that's the number of ways in which the black hole can assemble itself. Because the black hole is inside, really, if you look at it, it's really like an oscillating string. And that string can oscillate in so many different ways. And that number is given by this Ramanujan's function. But you know that a function like this, it's a geometric series, 1 plus x squared plus x cubed, if you remember, is 1 minus 1 upon x. So this function z of q is this very nice function, and it's called a modular form. It's a very symmetric function. And one of its very interesting properties is that z of t is related to z of 1 upon t, where t is defined in this manner. Q is e to the minus 2 pi exponential of e to the minus 2 pi t. So anyway, so using this very powerful symmetry, this is actually symmetry of a function. So normally if I give you a function, some function of x, it doesn't have any obvious symmetry properties. You cannot say that f of x is always equal to f of 1 upon x. But you know some special functions, like a symmetric function. F of x is equal to f of minus x. That's one kind of symmetry. So symmetric functions are give you a better way to tackle this function. And these modular forms are highly symmetric functions. And Ramanujan was kind of a master of it. And using the symmetry of these functions, he was able to deduce that for large n, the density, so the number of ways in which this number can be partitioned, or the number of ways in which a string can oscillate, goes exponentially as 4 pi square root of n. Now, this might immediately ring a bell for you, because this means that if I take the logarithm of p of n, it will be 4 pi square root of n. And that should match with the entropy of the black hole. And indeed, fascinatingly, this is exactly what happens. If you take the logarithm of p of n, 4 pi square root of n, it actually matches beautifully with Hawking's calculation, which has absolutely nothing to do with this integer counting problem. So this is one of these fascinating things in science, where completely unrelated areas come together and they are brought together and have a connection between them. And that's one of these aha moments that you experience in your research, that it's quite spectacular, that something to do with how do you partition an integer has something to do with the properties of a black hole, the area divided by 4 of a black hole. And all that depends on these notions like event horizon, speed of light, which Ramanujan knew nothing about. Okay, so I think I will maybe skip this. Ramanujan's mathematics actually comes into play in some other very interesting context. Some of the research that I've been doing in the last 10 years. Ramanujan wrote a very famous last letter in 1920, and he introduced new functions called mock theta functions, and which he said that are not like theta functions, but they are like look like theta functions. And again, that very exotic mathematics, nobody thought that this would have any application to physical problems, but comes in the problem of trying to understand the entropy of certain kinds of black holes. And so this I will skip. So anyway, I think I will stop here. I hope I have given you some kind of a glimpse of what is happening in some frontiers of physics, where people are trying to unify general theory of relativity and quantum mechanics. And why black holes are interesting is because black holes are one place where both general relativity and quantum mechanics are important. See, if you're trying to marry two things together, you need to context where both these things are on the same footing. In your semiconductors, you can more or less ignore gravity. or when you're dealing with a star, you can more or less, or a big, fat object, you can ignore quantum mechanics. But black hole is one place where quantum mechanics and general relativity are both important. And therefore, that's the reason physicists are interested in it, like myself. And which is why black holes have proven to be very useful guide in our search for the final theory of quantum gravity, because even though we don't have direct experiments, following Boltzmann and following the ideas of entropy, we can try to get indirect evidence for whether the black hole behave like normal objects, what are the constituents of a black hole, things like that. And there have been many intellectual conceptual advances following this theme of black hole physics. And this has been an exciting frontier of research in theoretical physics. I think I'll stop here. And I think maybe I'll stop sharing.
Okay. Thank you so much, sir, for this wonderful talk. If anyone has any questions, then you can raise your hand so that we can. Yeah. Okay. Vinayak, you can ask your question.
So, what will be medium required for oscillating string?
In vacuum, right? They are like fundamental things. What is the medium for oscillation of an electric field? Electric fields oscillate in vacuum. Yeah, this is right. There is no ether. See, before Einstein, people thought that, okay, what does the electromagnetic field oscillate? What is it an oscillation of? And they imagine that there is some substance which is oscillating, because normally when there is an oscillation, so fundamental strings are basically the substance. They're fundamental, so they make up the whole universe, and they are oscillating in vacuum, much like an electron is moving in vacuum, right? When an electron is moving, it is not moving in some medium; it's moving in vacuum.
Okay. Baljit, you can unmute yourself.
Yes. So when you were initially talking about how the force of gravity moves at the speed of light, I was asking, why does force need to have a speed? Like the ultimate speed limit is for light, because light travels in forms of waves or photons.
Yeah, no, it's a good question. I was a bit sloppy. I should say how does the influence of gravity? How does it's not the force of gravity, but what I want to say is that how does the influence of sun on earth change? Suppose if the sun disappears, or if suppose there is that influence should travel at the speed of light, right? But if you apply Newton's law of gravity, it tells you that, if you remember your Newton's law of gravity from high school, there is no time in that equation. It tells you that the force of gravity is equal to mass of one object, mass of the sun times mass of the earth divided by radius square. So it is instantaneous. The influence, according to Newton, travels instantaneously. Gravitational influence is the more correct way to say it.
So when Einstein actually talked about the universal speed limit as the speed of light, does that apply to just particles or waves, or does that apply to literally everything?
Yeah, everything. You cannot, no physical signal can be, there can be no physical transfer of energy faster than the speed of light.
Because we have read that a few matter waves can sometimes travel faster than the speed of light. Matter waves.
No. I mean, it can be that in a medium, the speed of light is lower. Okay, that's a different story. I'm talking about speed of light in vacuum. Yeah, it can happen that in a medium, the speed of light is not 300,000. Like suppose you take like a Cherenkov radiation and some scintillator or something. You know, there are of course situations where the particles can move faster than the speed of light in that medium, but not from this universal limit.
Sir, how many questions?
Not in vacuum.
Sir, how many questions can we take? So, you have a meeting.
Yeah, no, we can, if you can, yeah, I have 10 minutes or
Okay,
10,
okay,
15 minutes.
that's great,
Yeah.
that's great. So, Yokesh, you can ask your question.
Thank you. Sir, I actually love to ask two questions, sir. And the first question is, inside the black hole, the entropy gets lower since the degree of freedom is reduced because particles are compressed into a point, singularity point. So entropy also naturally gets reduced. So according to thermodynamics equation, uh, it should emit energy, no, sir. So does it pave way for white hole existence?
Okay, I think that's a good question. I mean, see, you might have thought that the entropy that Hawking was talking about could be explained by the entropy of the gas forming the sun, right? After all, a black hole formed by collapsing of the of the sun. So clearly, you know how to calculate the entropy of the sun because there are all kinds of atoms inside, and you can understand, apply their standard calculations of, quantum mechanics, and it turns out that the entropy that Hawking is talking about is enormously bigger than the entropy of the sun or the star, which might have collapsed to form it. And it is really telling you something about really fundamental properties of the structure of space-time at the Planck scale. And it has absolutely nothing to do with the entropy of the matter which has collapsed to form the star. It's much bigger than. So the matter which has collapsed to form the star cannot explain the entropy of the black holes. So that's one of the puzzles, that why does this object have such enormous entropy?
Says about entropy of a black hole is different from entropy inside black hole, no, sir. Entropy of black hole, the accretion disk and all the gases surrounding it.
That has nothing to do with this entropy of Hawking's entropy, Bekenstein-Hawking entropy that I'm talking about. So if you take, suppose you take a star which is just a little bit bigger than the event horizon, which is about to form a black hole, then it has a lot of entropy. There is accretion, there's all kinds of things are happening there, right? And it's still a star, so you don't have to, once it collapses and forms a black hole, then all that entropy is gone, it's inside. And you're right that maybe we can try to calculate that entropy will decrease or what will happen. In fact, that's a good question, in fact. This is one of the puzzles, right? It would seem to you that you can violate the second law of thermodynamics because by your reasoning, right? Suppose I throw the Encyclopedia Britannica Volume 1 or Encyclopedia Britannica Volume 2. Once it goes inside a black hole, I don't know which volume of encyclopedia I threw in. So the information, the number of ways I can write on this Britannica seems to be lost. Entropy seems to have decreased. And in fact, so it's a very good question. The question that you're asking is the kind of question that Bekenstein is asking. That how can it be that if I throw a hot bucket of water inside a black hole, then I have lost all the entropy of the bucket of water because the black hole. But the answer that Bekenstein gave is that no, but the black hole has entropy of its own. And once the hot bucket of water falls inside, its entropy goes up a little bit in such a way that the net entropy, the second law of thermodynamics, the generalized second law of thermodynamics, is actually observed. So this was actually the reasoning by which people first tried to figure out why the black hole must have entropy.
Thank you, sir.
Sonal, you can unmute yourself and ask your question.
Thank you. Sir, it was a wonderful session. What my question is, at one point you talked that the gravitational waves that we detected by LIGO detector were from black hole merger that happened billions of years ago. So how do we know that the exact time when it happened?
Okay, I mean, no, this is based on, it's a quite a complicated analysis of simulating a black hole, right? And basically you see how much energy you're receiving here. See, if it happened very close to you, you will get a huge blast of gravitational energy, right? But you're not getting that huge a blast. So basically, it's like a light. No, light becomes dimmer and dimmer because it's 4 pi r square, and the flux has to be conserved. So as you go farther and farther and farther, you get only a little bit of the light that is actually emitted. So from that, you know the distance of the. So it's a kind of a. There are many things that you can measure in this gravitational wave detector, and then you have to do a parameter fit, assuming masses of the black holes, the distance between us, and this is the best parameter fit. I mean, you have enough data to determine all these parameters. And nowadays, there are multi-messenger observations that you can observe the same event also in if it's a neutron star, for example, merging with a black hole. You can observe in radio waves, or you can observe it in different channels. And so you can be sure that it's not just, you're not relying only on general theory of relativity.
Ekta, please go ahead.
Okay, can I suggest actually maybe all of you can turn your video on and you can take a picture.
Yeah, sure.
And I mean, while we are asking questions, it's good if people.
Yes, sure. We will do that.
So I would request all the participants to turn their videos on. If it won't.
Just a second, Ekta. If possible, can everyone please turn on the video?
Yeah, I don't want to eat into your bandwidth. Okay, so.
No, that's no
problem. Yeah, go ahead with the questions.
Right. So you mentioned that it was not the force traveling, but it was the influence that was actually traveling. So I was wondering what the influence could potentially include. Like what factors are we looking at when we say influence traveling? What
influence meaning
right?
Right. If I wave my hand here, right, does it change the gravitational field experienced by the moon? It should, right? Because the gravitational field experienced by the moon depends on the total mass distribution on Earth and how it is distributed. So when I wave my hand, the moon should feel it will not feel exactly the same if my hand is here, if my hand is here. And that influence is extremely weak, so nothing changes really. But that actually, when I wave my hand, I'm creating a gravitational wave. But it is so weak that you wouldn't be able to see it. And that will go and hit the moon. And then there will be, but the effect is so small that you wouldn't be able to detect it. But if a black hole moves, two black holes move, then the effect is like a giant hand is being moved. And then that influence can be noticed, that change in gravitational field. See, another way to say that is the gravitational field produced by two black holes is different from the gravitational field produced by a single black hole. Right? So when two black holes merge into each other, the influence of that gravitational field, how is the field changing? And very much like how the electromagnetic field, the electromagnetic influence travels in electromagnetic waves, right? When you turn on a mobile phone and send a message, right? You are sending a signal. Basically, think of it as a signal. The gravitational signal travels at the speed of light, much like an electromagnetic signal travels at the speed of light.
And that signal is the gravitational wave.
Yeah, that signal is the gravitational wave, just like the signal sent from your mobile phone is the electromagnetic wave.
Right. Thank you.
So can we take one last question?
Yes, please.
Okay, Varun, you can go ahead.
Yes, sir. As entropy is the only quantity which can distinguish between forward and backward motion of time, so can we say that the entropy is quantized because of the quantized nature of time, line time?
No, well, it's not true that time is quantized, first of all. And that's not a precise enough statement. But entropy is quantized. In quantum theory, the entropy is actually logarithm of a quantity which is quantized. The number of ways. But the number of ways is a number, right? It's a natural number, right? It's an integer. So entropy is a logarithm of an integer. That's very surprising because see, entropy is a quantity that you measure using thermometers and heater and so on. There are no integers there. But fundamentally, there is an integer there, which has to do with the number of ways in which the atomic constituents are constituted. And in fact, in the black hole context, this is one of the things that I have been involved in. You can actually calculate that integer precisely. And you find that it agrees, actually. The entropy is, in fact, quantized in that sense.
There are many more questions, sir. So I guess what we can do,
Maybe we
compile the questions.
Maybe we can, yeah, we can take maybe one more and then I will leave.
Okay, that's great. So we can take one last question if I guess Yokesh had one question. If you could just okay.
Okay.
Sir, am I audible?
Yes, please go ahead.
Sir, actually, so even after the consideration, the dual particle nature, wave nature of gravitational waves, it seems to be have a speed of propagation and frequency or intensity, sir. Like intensity depends on mass and properties of a gravitational wave with its origin, like black holes, like any other wave. So similarly, black body radiation, there's a quantized form of emission, such as even if you provide energy beyond a certain limit, instead of emitting a less high energy photon, it emits many low energy photons. Like there's a graph of distribution for black body variation. So is there anything exist like that, sir, similar to gravity, gravitational wave or gravitons?
Yeah, so gravitons actually, I mean, this is something you cannot measure, but if gravitons were thermal, yeah, this is a highly theoretical situation. But this Planck distribution law simply follows from the fact that photons are these bosonic particles. They're bosons, the Bose particles. So from they are free Bose particles, and from that you can actually derive the Planck distribution formula. So gravitons are also bosons. Therefore, gravitons, if they were in thermal equilibrium, see, it's very difficult to bring the gravitons in thermal equilibrium. But if you could bring graviton in a cavity in a thermal equilibrium, they would also obey Planck's distribution formula. But it's a highly, see, because light you can confine to a cavity, because if it hits the cavity, there are electrons which stop it. Gravity will just pass through. There are no walls that can hold the gravity back.
So a particle can absorb a gravity, sir, and loses its energy actually.
Yeah, but I think it's that interaction is so weak that to thermalize the gravitational radiation is almost not going to happen in your lifetime. So.
Thank you, sir.
I would like to request Dabade ma'am to say a few words.
Well, good morning, sir. From here, it's hello, and
hello,
I'm really thankful because we finally made it. Since last year, I think we are trying to have your invited talk since you took up the responsibility as the director of ICTP. And we were really extremely happy that you happened to be a Fergusonian and all the students really wanted to have you as an invited speaker last year for Frontiers in Physics, which was offline. And we were hoping that if you come down to India sometimes, come down to Pune sometimes, and then take part in Frontiers in Physics. But this year, at least, the positive side is that because of these online lectures, we were able to hear you. So we really, really thank you and invite you to Ferguson College once again. Whenever you come to India, do drop in. So thank you again. And I'm really thankful because I know you had a very tight schedule and you managed to give us time of more than 1 hour. And I'm sure the students enjoyed it.
I appreciate it. Thank you for the invitation. It's been a pleasure to virtually visit my Ferguson College. And I do actually, when I come into India, normally just visit Ferguson and Vaishali and so on.
Please.
So I'll be happy to come by. Okay.
Thank you, sir. Thank you.
Thank you. All the best to all of you.
Hello, am I audible now? Am I audible?
Yes, you're audible.
Okay. So I just want so thank you all for coming to FIP, and now we will have the oral presentations, and they will start from 4:45. So hope to see you all then. Thank you.